Okay, thank you very much for the introduction. So, yeah, my name is Paul. I'm very happy to talk on behalf of my team on opportunities for system-level technology assessment at Imec. Let me first transmit the main idea of this whole talk. You see here 3 steps, 1, 2, 3. So what we are proposing is to go from TCAD models via Liberty files to critical path timing reports. This per se is nothing new. This is a standard design flow, but we are proposing to accelerate this a little bit to have particularly skipping compact modeling and skipping resynthesis to have a somewhat faster loop from TCAD to to the impact on system level to eventually even circle and change the options and see what happens in a fast way. At this point, I think I should have to clarify that the title of my talk is not SRAM. Sorry about this. This is because I changed internally in Imec since the invitation to the workshop. And one requirement of my new management was that I will talk about my new world and not about my old world, and to have 1 or 2 slides about my new world. So I'm going to talk about Imec services and technology targeting services within Imec services, within Imec. And then we'll go into the 2 points more deeply, so from TCAD to Liberty files and from Liberty files to timing reports, and conclude the talk with a summary. So what are we? We are technology targeting services. Our typical client or customer is a small or medium enterprise design house which has a design IP, and it's not always clear for them what kind of technology they should go for. And we thought this is an opportunity for a business model, and we provide consultancy. We make custom tools to help them in the decision what design they should choose, and hope then that they will tape out with us, of course. This is a good example of the tools that we make to support our decisions. So everything is based around access toolboxes for the different formats that you find in a typical EDA flow, from SPICE to Liberty, GDS2, which can extract important information for the design, specific to their design. It further comprises tool development using those access toolboxes in custom ways. And it also comprises tool deployment. This can happen in our site or at the customer side, and all kind of site services like licensing, training, custom solutions. I will talk more about this toolbox thing later on. We'll give an example in the Liberty to critical path section. All of this is happening within Imec services. So this is a part of Imec which is not dealing with future technologies and processing and CMOS, but is providing services for established technologies. So it has 2 big components of design services, front-end, back-end, and also foundry services for TSMC, UMC, ON, and AMS, and the described technology targeting services. So the main part of my talk is actually stemming from our technology targeting solutions. What a typical problem of a client is, look, we have so many process providers like Global, Samsung, TSMC. Which one should we take? And if we know which one we take, which supplier of a standard cell library should we take? There's TSMC, there's ARM, there's Synopsys. Each of them has several options. You have 7-track libraries, 8-track, 9-track, 12-track, And then we have process flavors, VT, LVT, SVT, HVT, super HVT, this all combined with different gate lengths, offset plus or minus, multiplied by the number of supply voltage options and the number of process corners and the number of temperatures. And you're pretty screwed. You simply don't know where to start, what to take. You can compare it a little bit like tasting a fine wine. Tasting a fine wine is expensive. Therefore, you cannot taste them all. If you try to do that, you will probably end up in a headache. Right? I've been discussing if this headache is coming from the wild mixing of wines or from the money you have to spend to pay the wine. Whatever it is not a viable solution. But there is a solution to this, and it's actually not very new. It's the concept of brokerage. This is actually a medieval wine broker, this guy on the right side. And on the left side, there are two clients. And before they are going to buy a full barrel of wine for lots of money, the broker is providing samples using a specific tool. So they can taste whether they want the 28 nanometer flavor or the 40 or the 65 before making a product or before buying an expensive technology. Now, this story was actually a result of our technology targeting service with existing models. I was wondering how could I change this story to be more applicable to this workshop today. It's about TCAD, and it's in Glasgow. And now we have a hang. There it is. The only difference I saw, we are tasting whiskey, but all the rest still applies. You still have at the input some technology option, whether it is a FinFET or a bulk or a 3.5 or a more crazy one, like we just heard, it's still the same problem. The only component that is missing is a correct Liberty file of the technology that we want to investigate, and all of the rest of the flow will still apply. So the main part of the talk is now about this tool that the person is using, which should make our life easier to correctly sample wine or whiskey in this case. And this will happen in two main steps. So first of all, we propose a rapid TCAD to Liberty flow. I think it's important to go through this background very quickly. So what is Liberty? Liberty is a quasi-industry standard for many, many years for digital design. It can be used to drive synthesis, and it is used to do static timing analysis in a quick way. And the key of success of Liberty, in my opinion, is simplicity of the timing models. At least in the most simple form, it's taking just a 2D lookup table to compute the delay of a certain cell. So, for example, in this XNOR gate example, we have a delay arc from input A1 to the output, and the timing model tells you how long this will take if the input rise time is this much and the load is this much. So it's a two-parameter model. So you need a 2D lookup table plus interpolation, which makes it an ideal application within MATLAB. So the question is how to get to those Liberty files. Well, in the classical way, you need a compact model and a standard cell netlist, and then you run the characterization runs that we heard before, which takes a lot of your CPU time. Maybe not the most, but very much. If you add corners, temperatures, and so on, it's really a hard job today. Of course, everyone is talking about variability today, so if you add variability, which you can do nicely if you have the nice models, But unfortunately, if you put this in a Monte Carlo loop, it will not take 5 days, but 200 times 5 days to get a statistical idea of full liberty files. It is possible to do it in this classical way. We have demonstrated this in cooperations with University of Glasgow. But we were thinking, wouldn't it be possible to do this directly? So to go from TCAD to Liberty directly. This is more a proposal to this workshop. We don't know it. We know there are companies which claim on their websites you can do a NAND gate or a flip-flop in TCAD directly. And then we thought, okay, maybe why not do this for all cells that you have in a critical path? And if you have the statistical capabilities, why not also do it statistically? If it's possible or not, I don't know. But we see the possible benefits. You would skip a statistical compact modeling step, which we heard many times today is a very hard job to do. You would skip statistical cell characterization, which is a very CPU-intensive job to do. And you could save additional time maybe by not only excluding the cells you don't need, but also excluding the arcs you don't need. For example, if in your timing path an XOR switching on the A input pin, don't characterize the B pin because you don't need it. Okay, again, this is more a proposal part of my talk. Now coming to the next part. So once we have Liberty files, be it via the classical way or the maybe faster way, how to go there to critical path analysis in a rapid way. And one of those rapid ways is the one I would like to propose. It is based on our toolboxes and it's called timing traces or power traces, because you can also do it for power reports. A critical path, if you have a chip with hundreds of thousands of cells, but only maybe 40 or 50 of them connected together determine the performance of the chip. So this is an example of one of our in-house LDPC decoders, and you see highlighted the few cells which actually determine the maximum speed of this chip. Usually you put this in text form, so you have two examples of a text form of a critical path. The two main EDA tools are Synopsys and Cadence. On the left side, there's a critical path with one cell between two flip-flops. This is simply because a longer critical path did not fit on the page, but is enough to explain the concept. And on the right side, just to highlight, this equally works with memories in the critical path. The same thing with a DRAM instead of a flip-flop. So it's always the same. You have a sending flip-flop and a receiving flip-flop, and then a certain number of gates in between. And with a simple timing model, it's relatively easy to accumulate the delay along the critical path in order to get the maximum clock period you can spend between these two flip-flops, and therefore you can determine the maximum clock frequency of this design. Now, what we have been thinking, how can we help our partners to change the library within such a critical path? And this is our concept. What we basically do, we take a reference timing report from one of our clients, only the timing report. With our tools, we convert this timing report to an executable, and we can send this executable back to our client. The client can now execute the executable with a parameter of a new Liberty file and will get immediately on the command line the updated timing. Now, this has two big advantages. First, we don't need the design IP from the client, so there's no IP NDA issues whatsoever, because we only just have the critical path. And secondly, it's fast. So since we are avoiding a complete resynthesis of the design, we just update the timing of the given critical path, so to say. Therefore, the whole thing is largely independent of the design size, and typical runtimes are in the orders of seconds. Of course, you might say, yeah, but how about accuracy? If you compare this to a full resynthesis flow, and then our answer is actually not so bad. You can look in this diagram here. This is an accuracy assessment. The cumulative delay along the delay segment of a path of a DSP in this sense, in this case. So in blue, you have our re-evaluated timing trace with the same library as in the original timing report, which is there in red. And the differences are really in the 1% area. Here in the background, you have example how this looks like. So you have on the command line the name of the design, and then as a switch, the new library, and you will get the updated timing path from the executable in a quick way. We even made a YouTube video out of it, so if interested, just enter these 3 keywords into YouTube, and you will get a demo session of this concept. So here's more accuracy benchmarking. This is where we took a part of the 40 nanometer libraries that we found on our disks and switched the corners on them and compared it to a full resynthesis. And we always came up with about 1% accuracy for intra-node accuracy. If you change technology node, accuracy is a little bit worse, but still acceptable, around 2%. Another example is, so we are also trying to convince TSMC how useful this is. So because TSMC today has in their data books these general scaling ideas. So if you take your product from 65 nanometer and you take your same product and convert to our 40 nanometer nodes, you will gain this much in speed and this much in leakage. However, what this data book does not tell you for what design this is. It could be a ring oscillator. It could be an ARM core. They simply don't specify. But with our technique, you could do this in a more design-specific way, saying, okay, for this finite state machine or for this FC controller, you could get these more detailed numbers when you switch technology node. Okay, final example that we did with this thing was on 28 nanometer LDPC decoder from before. And then populating this graph on the x-axis with maximum frequency and the power consumption with all of those 28 nanometer flavors that we had available. And this simply helps the designer to choose which is the right one if he knows what is the constraint for frequency and energy per bit per operation. I already mentioned variability is important. Everyone is talking about it, so even we are not blind on this. And what you see here, these thick arrows, this is actually work in progress. So there we are trying to find not the worst case solution given by the technology corner, but the 3 sigma optimal one. This is only possible if you have detailed statistical data available. But I think we can have it from TCAD level, and therefore the whole variability concept from TCAD is important to have it, but we can translate it to Liberty and then further to variability assessment on system level. And so this builds the final chapter of this talk. So about variability, we are aware. And the good thing about our traces in this respect is that it's fast. So you have about 1 second update for the critical path because the timing models are simple. So why not do this statistically? So if you put in statistical libraries, you will get a statistical timing trace, and you will get a distribution of your critical path timing, which is what the partner wants to know in this case. Of course, the problem here is pushed to the statistical library access. How do you get those? I've been already talking about these. If you do cell characterization, it's very slow. If you do it statistically, it's very, very slow. If you do it in TCAD, we don't know. But timing traces gives you the possibility to only recharacterize those cells which you actually need. So even those which are only unique cells in the path need to be recharacterized. And from those, only the unique arcs. So there's a potential saving here to make. But let's assume we have it. Once we have it, you can produce nice pictures like this one. So it gives you the path delay distributions for the first 100 paths in a FFT design, or here on the right side for the LDPC that we had already. And in addition, we have this color code on the amount of logic depth within the path. So the message should be here, variability is important. Knowing local variability is very important for design. And we know statistical or atomistic TCAD can give us local variability, as we did many times with Professor Asenoff. We did it at that time for SRAM, but even for logic design, it's kind of important. If you consider these nice effects that you only have with local variability, such as the parallel path effect. So if you consider these blue curves are the first 50 critical paths of a DSP processor. The one in red is the critical one in nominal case, but in the statistical case, you have to take the worst out of the statistically worst. And this will give the well-known effect of shifting the arrival time distribution to the worst delays. But there are other effects. If you don't know your clock tree variability beforehand, you have to estimate it. If your process variability is bad, then you have to apply more margin. So you have to keep margin for setup and hold time fixing for later on, and this costs you always area or power. And I already talked about SRAM stability, where we also had projects in the past with us and Asenoff. Local variability also propagates through a path. So many people think it gets worse. It's true and it's not true. So in absolute terms, variability, local variability spread increases. It increases, but it doesn't increase additively. It increases by the square root of n. But it doesn't decrease, so it's an important difference. So we've seen local variability is important, but how about global variability? Here we have to say clearly, global variability is at least as important as local variability. The reason is that it's actually true in the sense that local variability cancels out if you put it in front of global variability. Since global variability adds up in absolute terms, local variability has this canceling out effect along the path. So if you look at the end of the path, global variability has still the same in percent as in the beginning. as opposed to local variability, which has decreased in percent. You can see this very nicely here. This is the global and the total variability for a single cell. So you see that the total variability and the global variability are not the same. So the global is smaller, so you still see the local component in the total. And for this reason, for a single cell, a slow corner is appropriate to measure the worst case timing. However, if you look into a critical path with more than 20 cells, then if you compare global and total variability, you see they have pretty much aligned to the same spread. And this is because the local component has cancelled out along the path. So for critical path analysis in the first order, if we have no parallel path effect, the global variability is much more important. And we would therefore propose that TCAD modeling takes this into account, but I've already learned today that it's already done, so this is actually good news for such kind of exercise. I'm already at my summary. So I have presented ideas for rapid flows from TCAD to via Liberty files to critical path models. For TCAD to Liberty, the idea is to use TCAD directly to characterize standard cells. You will avoid statistical compact modeling. You will avoid cell characterization. If that is feasible or not, we don't know. But once we have Liberty files, one way or the other, we can use our methods to quickly translate this to critical timing path updates. These are called Tetris tools. They are generated from timing reports. They are accurate. They support memory, multi-VT, and you can assess a foundry change or technology change directly on the system level and identify the best option for your design. About variability, we have learned local is important, but global is at least equally important. So a more concise summary of this talk is, if you taste in a wise way with the right tools, there will be no headache.